64. The long straight wire AB that looks like this carries a current of 14 amps this way. Boop, boop. A rectangular loop whose long edges are parallel to the wire, like so, carries a current of 5 amps that goes this way. Find the magnitude and direction of the net force exerted on the loop by the magnetic field of the wire. Okay, so this distance here is 2.6 centimeters. This distance here is 10 centimeters. And the length of our loop is 20 centimeters. Okay, so this wire is the one making the magnetic field. So follow our thumb everywhere on the bottom side of the wire. It's going into the page. Boop, 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 boop. So this stick and this stick are going to have a constant field along the whole thing because they're at a constant radius from this guy. Luckily, this guy and this guy are going to cancel each other out because the current in one is the opposite direction of the current in the other. So we don't have to worry about any of those radially dependent fields. So we only need to look at this guy and this guy. So for the top chunk of my wire, the force on a current carrying wire is IL cross B. So B and L are perpendicular to each other. So this is going to be ILB. B of my current carrying wire up here is going to be mu naught I over 2 pi R. Okay? So now for the closed wire, my force is I, which is 5 amps, times L, which is 20 centimeters. Mu naught is 4 pi times 10 to the minus 7, some units I can never remember. I of the thing making the field is 14 amps over 2 pi, and then the distance here is 2.6 centimeters. All right. So the magnitude of the force that this dude is putting on the loop, 5 times 0.2 times 4 pi times 10 to the minus 7 times 14 divided by 2 pi times 0.026. It's going to be 1.077 times 10 to the minus 4 newtons. And we can look at the direction of that using our right hand rule. So IL is going, there's this guy, so it's going this way. B, we found out before, was going into the page. So into the page. So that's going to give me a force upwards, which we can check because wires, unlike charges, if they go in the same direction, they attract each other. Cool. So for our wire, our force is going to be 5 amps. The length is 0.2. Our field is still mu naught I over 2 pi, but now my R is 10 centimeters. Okay. So plugging that in, I get 2.8 times 10 to the minus 5 newtons. Okay, so this one, my IL is this way, my B is into the page, so my force is going to be going down. Now again, for the two sides, one's going this way, one's going this way. Same length, so they're going to cancel each other out. So I don't have to worry about them. Okay, so now if I sum up my forces, I've got 1.077 times 10 to the minus 4 newtons going up, and then minus, because it's going down, 2.8 times 10 to the minus 5 newtons. So this minus this is going to be 7.97 times 10 to the minus 5 newtons upward. And double check. This one's closer, so this one's going to win. These are attractive, so my force should be attractive. Huzzah!